Hello, everyone. Welcome to the series on F singularities, where in this session we are going to look at the theorem of Kunz, which says that a ring is a ring of Noetherian ring of characteristic P is regular if and only if the Frobenius on R is a flat ring map. So we know that regularity is a local property, and the Frobenius being flatness is also a local property. And not just that, because the Frobenius map on local rings is flat if and only if it is faithfully flat. We have this uh, two equivalences. That R is regular if and only if Rn is a regular local ring, and similarly Frobenius is flat if and only if F localized at M is a faithfully flat Frobenius map. So we may assume that R is a local ring and then show these two regularity and Frobenius flatness are equivalent. Okay, so right, let's just start writing here. This is going to be lecture. And then is 19,186. Right. So let's proof of this implication that regularity implies Frobenius is flat. Suppose R is regular. Now, what we know about regularity is that its completion is also regular. And so if you want a very a sketch of that proof, it's just dimension of R is dimension of R hat is equal to dimension R. But by regularity, it is going to be the number of generators of the maximal ideal, and that is equal to the number of generators of the maximal ideal in R. Therefore, the regular. Okay. So, moreover, uh, R hat is also equicharacteristic. Equicharacteristic means that the ring and its residue field have the same characteristic. That is, R hat and R hat modulo M R hat, which is just K, have same characteristic, because as we saw in the first lecture, the uh, characteristic of the residue field divides the characteristic of the ring, but the characteristic of the ring is P. Therefore, the characteristic of the residue ring must also be P. So yeah, this is the equicharacteristic. Hence, by Cohen structure theorem, R hat is isomorphic to K x1 xd, where d is dimension of R hat. So for equicharacteristic rings, it's isomorphic to a power series ring over a field. For mixed characteristic rings, it's isomorphic to a power series ring over a DVR, complete DVR. So that is why we need the equicharacteristic part here. Okay. So now, what is the Frobenius of applied to R hat? It's R hat power P, which is K power P of x1 power P dot xd power P. And I have mentioned in the last session that um, to check that Frobenius is flat, it is equivalent to check whether R hat is flat as an R hat power P module. So that's what we are going to do now. We are going to show that this R hat, which is the power series ring over a field, is going to be flat as R hat power P module. Uh, it's not difficult. It's very easy. Like once you see that, you have this inclusions k x1 to xd. Okay, so we have inclusions. This which contains k x1 power p xd power p, which contains k power p x1 power p to xd power p. And this is r hat, which we know. And this is not known. We don't have a name for it, but this is going to be r hat power p. Now, this particular, just write it on different. So this is free. This is a free extension. Why? Because these are monomials of power p. So this inclusion, you can prove it in one of two ways. One, you can show that this subalgebra is also a power series ring. Therefore, this extension must be a free extension. Or just simply by looking at um, the monomials uh, x1 power I1 dot 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 x b power id such that 0 less than or equal to ij less than or equal to p minus 1. This form a basis. So therefore this extension is free. And yeah, this is part of one of the exercises that I posted in the drive link. So, and this extension is also, maybe I should write it like this. So this is a free extension because the it is just base change. You're going from k power p to k, and the k both are fields, so therefore this is a free extension, which means hence r hat is a free r hat power p module. So okay, uh, so it's a free r hat power p module, hence uh, uh, hence a faithfully flat r hat power p module. Okay, so this is good, but now we want to bring this property down to R. And so that requires a very clever way of looking upon it. So what is R hat power P? Now I claim that this is actually R power P hat. So with I hope that you've seen some uh, completion and results before. But note that so uh, the maximal ideal here is going to be m power p r hat. Okay, and here it's going to be m power p again. So these two rings, because they have the same you can get an isomorphism by looking at the ring R power P um, will have M power P as its maximal ideal. And that is again a maximal ideal with all the cofiniteness property that you have. Sorry, not cofinite. So not cofiniteness, what am I talking about? Okay, so um, this completion is um, you can take a completion with respect to M power P, and that is cofinal with the topology with the filtration of M itself. So you have this equality. Ultimately, yeah, you can go check it out. This R hat has filtrations. Let me just write it informally here. So R hat has filtration uh, M, which contains M square and so on. At the same time, R power P has filtration for its completion. It's M power P, M power P square, and so on. And these two filtrations are cofinal, which means that they induce the same completion. And yeah, so well, I don't think it's sorry, it's not R hat, it's R, but yeah, I guess that is not really confusing. Sorry. So now this R hat, R power P hat is just this tensor. So you have seen this before in completion. Wait, sorry, wait, let me just rewrite the proof a bit because this is not true with if R power P is not R power P, yeah, sorry, yeah, yeah. Let me write it in a different way. So this is what we have. We have R power P and R power P to R. This is the inclusion. And we have uh, R power P hat, which is R hat power P. And this is another inclusion inside R hat. And we have this vertical map. Okay. So yeah, this is R hat. Now, so if we look at this, yeah, if we look at this, the inclusion at the top, this is faithfully flat, which we just saw. This is a completion. This is also a completion. So these two maps are faithfully flat by the property of completions. So this is a faithfully flat map. Yeah. Sorry for the confusion. So this is the hence R power P inside R is a faithfully flat extension. Hence F is faithfully flat. Right? Okay. So now we have to show the converse part that Frobenius being faithfully flat implies that R is regular. So before we show the converse, we need a lemma. So this lemma is due to Lick, and let me just define what the lemma is about. So our situation is that let Rm be a local ring. We say that the elements, the set of elements x1 through xn is Lick independent if a1 x1 dot 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 an xn equal to 0 for some AI in R, then AI belongs to the ideal x1 through xn for all 1 less than or equal to I less than or equal to n. So if you've seen a regular sequence, this is a slightly weaker condition than the elements being regular. Because regular, so let me just write that as a remark. So remark is if x1 through xn is our sequence, our regular sequence, then it is leg independent. And the proof of this can be found in Matsumura. Actually, the converse is, there is a converse to this. Conversely, if x1 through xn is leg independent and the ideal uh, I, which is x1 through xn, as finite projective dimension, projective dimension, then uh, x1 through xn is a regular sequence. This is due to Vascon Vasconcelos, I think Ferrand. So proof in Brunson-Hauser. Brunson-Hauser. I think I've mentioned this in the exercises. I'm not sure now, but um, also this is an if and only if statement because if you have a regular sequence, um, the projective dimension of the ideal project, moreover, if I is equal to x1 through xn, then projective dimension of I over R is equal to n, which is finite. Why? Because it's the Koszul complex of x1 through xn is actually a resolution for R mod I. So therefore, this has finite projective dimension and it is leg independent. And conversely, if it is leg independent and it has finite projective dimension, it must be a regular sequence. So that is uh, a relation between the regular sequence and leg independence. Uh, so we need this slightly weaker condition of it being leg independent because what we are trying to show that when we want to show that a ring is regular, we first look at a minimal set of generators for the maximal ideal, and then we show that that is a regular sequence. So we can't directly assume that it's a regular sequence. You have to show that it's a regular sequence. And one way is to show that it is leg independent and then prove by some methods that it must be regular. Okay. So that is a remark about this. Now we will look at a lemma uh, due to leg. So let again R M be a local ring and x1 to xn be a set of leg independent elements. Not just that, which generate M primary ideal. This need not be a system of parameters in the sense that You don't need to have exactly D elements where D is the dimension of the ring, but it must be an M primary ideal. Okay. Suppose the first element x1 is y1 z1 for some y1 comma z1 in the maximum ideal. Then two things. First is that y1 x2 xn and z1 x2 to xn are leg independent. So it says that we can sort of, if you've seen regular sequence, then this is a similar property in the regular sequence, which says that um, when we want to show that the powers of regular sequences are regular, and there is a similar property with regular sequence like this. And then both yeah, y1 through y1 x2, sorry, y1 x2 to xn and z1 x2 to xn are m primary. Okay. Generate m primary ideals. And the last thing is a sequence. It's about the length. So the length of R modulo x1 x2 to xn, the length is additive. So it is R modulo y1 x2 to xn plus length of R modulo z1 x2 to xn. Remember that all three are M primary ideals. That is guaranteed by part 2 of this lemma. Therefore, the length are finite, and the third part says that the length are themselves additive. So we'll see this. Okay. So we show that the ideal x1 through xn, ideal quotient by y1 in R is generated by z1 x2 to xn. And by symmetry, the same is true for the colon ideal of the Z1. Okay. So we'll show this and we'll see how this proves everything. So note that Z1 x2 to xn, this ideal is contained in x1 through xn colon y1 because y1 z1 is contained in this ideal and x2 to xn are already in that ideal. Suppose A is an element in x1 to xn colon y1, then ay1 is equal to some a1 yeah, ay1 is some minus a1 x1 dot dot dot. Let me just, so ay1 belongs to this x1 to xn, hence there exists a1 through an in R such that ay1 plus a1 x1 plus a2 x2 plus an xn is 0. I'm just bringing, so ay1 is some R linear combination of x1 through xn. I'm bringing it to the other side, and then we have this equality. Now multiplying by z1, we get a plus, so az1, so not az1, ax1 plus a1 z1 x1. plus A2 Z2 Z1, A2 Z1 X2 plus AN Z1 XN is 0. Okay. Now, this particular, therefore, um, writing BI as Z1 AI, we have A plus A1 Z1 times X1 plus B2 X2 Bn Xn is 0. And we use the leg independence property. Hence, A plus A1 Z1 belongs to X1 to Xn. Now, this is contained in Z1 X2 to Xn, since the ideal X1 is contained in the ideal Z1, because X1 is divisible by Z1. Therefore, this ideal is contained in the other. And we have that A plus A1 Z1 is also contained in this ideal. Therefore, because A1 Z1 is already in the ideal Z1, ideal generated by Z1, we have that Z1 X2 to Xn. Remember, we chose an element in the colon ideal, and we showed that it is contained in Z1 X2 to Xn. Therefore, make it in different line. So, therefore, X1 X2 Xn colon Y1 is Z1 X2 to Xn. Okay. Right. So now we show that this element, this set, is leg independent. Okay. Suppose there exists A1 AI in R such that A1 Z1 A2 X2 AN XN is 0. Okay. Now multiply with respect to multiply, not with respect, multiply with uh, Y1 to get A1 X1 plus plus A2 Y1 X2 and so on until AN Y1 XN to be 0. Now we use the leg independence of X1 to Xn, leg independence of X1 through Xn. We have A1 belonging to X1 through Xn, which is contained in Z1 X2 to Xn. Okay. And AI Y1 belongs to X1 through Xn for all 2 less than or equal to I less than or equal to n. Hence, AI belongs to the ideal X1 through Xn colon Y1, but we just showed that that is Z1 X2 to Xn for all 2 less than or equal to I less than or equal to n. Therefore, AI belongs to the ideal X, not X1, Z1 X2 to Xn for all 1 less than or equal to I less than or equal to n. Hence, Z1 X2 to Xn is leg independent. By symmetry, the other Y1 through Yn is also independent. Similarly, y1, x2, xn is also like independent. Okay, so that's fine. And for part B, note that x1 to xn is contained in y1, x2 to xn, and x1 to xn is also contained in z1, x2 to xn. So both are M primary ideals. Because some power of M is contained in x1 through xn, therefore it must be contained in y1, x2 to xn, and also in z1, x2 to xn. So that is P. So now we look at the length formula. So we have the short exact sequence, which is 0 to r modulo x1 to xn colon y1. This is multiplication by y1, r modulo x1 to xn to r modulo y1 x2 to xn. So this is a very standard short exact sequence, which says that if you have a multiplication map on a ring, you have a multiplication map from r modulo I colon that element y to r modulo I to r modulo I plus y. So this is the short exact sequence. R modulo I colon y to R modulo I to R modulo I plus y to 0 to 0. But here in this case, the x1 is contained in the ideal of y1. Therefore, we can replace x1 with y1. I plus y is just y1 to xn. And on the left, you have the colon ideal. But since x1 through xn colon y1 is z1 x2 to xn, we are done. Because length is going to be an additive function. It is additive on short exact sequence, but the one on the left is just z1 x2 to xn. Therefore, we have the additive formula, this particular formula, length being additive. Yes. Okay, so now we are ready to prove the converse. So proof of the converse part. Okay. So suppose the Frobenius map is faithfully flat. Remember that we are working with local rings, so the flat maps are faithfully flat. So hence, it is injective. Thus, R is reduced because Frobenius is injective if and only if R is reduced. And we have that R is flat over R power P. In fact, since the Frobenius is flat, Fe, the iterated Frobenius from R to R, is also flat for all E greater than or equal to 1. That is, R is flat over R power P power E for all E greater than or equal to 1. Okay. So now, hello?
So at this point, like, okay, I should have asked this earlier. Like, whenever you say like the map is flat, like, from the third lecture. You said like map being
Yes,
flat and the codomain being flat over the image of the map. Uh,
not the same.
they are not the same, but here you can do that because it is injective.
Here, it is injective. Yes. So there is an isomorphism between the source ring and the image because of the
Okay. So because
injectiveness
of
of
that,
the
you can use that. Okay. All right.
yeah, because of that, we are identifying the ring with its image because of the injective property, and
All
then
right.
say that okay, it's enough to consider it as a subring. Okay.
Yeah.
Yeah.
Yeah. Yeah.
Okay.
And the
Uh,
Frobenius map on the regular rings will be injective.
yes, because regular rings are reduced.
Okay. All right. All right. Okay. Yeah.
Regular rings are reduced, therefore
Yeah.
the
Yeah. Yeah.
Frobenius is injective. Yeah.
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 Yeah. Yeah.
And
Yeah.
regularity is because regular rings, regular local rings are domains. Therefore, regular rings localized at any prime ideal is going to be a domain.
Oh, and
Hence
being
reduced.
reduced. Okay.
Hence
All right.
reduced. So that is why regular rings are reduced. So reduced is the local property.
Nice. Nice. Okay. Okay.
Yeah.
All right.
Okay. Okay. So now we are uh, so let Q be equal to P power E um, for some E at least one and define NQ, which is M intersect with R power Q. So this is going to be this is the maximal ideal of RQ. Okay. So RQ is actually local ring. So that is also clear. Moreover, what if we look at the extension of this ideal, NQR? This is the qth Frobenius power of n. Because if you look at the generators of n power nq, it is going to be powers of qth powers of r, which are also contained in n. And the ideal that it generates inside r is precisely the qth Frobenius power. Okay, now since r is flat over rq, this mq, the qth Frobenius power is nq dot r. There is this nice relation. This is true for all flat extensions that if if R to S is flat and I is ideal in R, then IS is isomorphic to I tensor or I tensor, sorry. It's IS is isomorphic to I tensor S over R. Just I okay, fine. Let's move on. Okay, so this property holds for flat extensions. So in particular, it holds here. So now MQ modulo MQ square. We'll see why we are considering this. Basically, we want to show that set of generators for M is like independent. And we will, oh, wait, did I make another remark? Uh, Okay, so I think I did not make one remark. Uh, what is this again? Let independence. Yeah. Okay, let me just make it along the way. Uh, so this thing is equal to NQR modulo NQ square R because it's the square of ideal. And this is now NQ tensored with R over RQ modulo NQ square tensored with RQ over R. And we know that this is a flat ring extension, therefore we can actually bring the tensor out because you have this NQ square to NQ to NQ mod NQ square to 0, and then you tensor this whole thing with R over RQ. And this because R is flat over RQ, this just still an exact sequence. Therefore, the quotient is precisely NQ mod NQ square tensor with R. So that is the whole reason. This is not true in the general case, but here because R is flat over RQ, we can uh, have this. Okay, right. So now this particular thing is now isomorphic to by a simple base change of tensors RQ over NQ of RQ over NQ, and then I'm tensoring this whole thing over R. So I'm just introducing an intermediate ring, RQ modulo NQ. And now we look at NQ mod NQ square tensored with RQ modulo NQ of this particular tensor, which is RQ modulo NQ tensored with RQ over tensored with R over R. Okay, so this is NQ mod NQ square, which is tensored over RQ modulo NQ of R modulo NQR. Now, why is that? Because this is a ring R modulo I, some S modulo I tensored with R. So this on the left, you have something like S mod I tensored with R over S. So this is precisely R modulo IR. Okay. So that is the property that we are using here. And this is exactly equal to NQ mod NQ square tensored with R power Q mod NQ of R modulo M Frobenius power MQ. So is this fine? Yeah. So, okay. Now we note that what RQ mod NQ is a field because NQ is um, precisely the maximal ideal of RQ, and N hence NQ mod NQ square is a free RQ mod NQ mod. Okay. So right. Moreover, uh, RQ is contained in R, which then quotients to R modulo MQ with the kernel of this composite being MQ M power Q intersect with RQ, which is precisely the maximal ideal of RQ. So we have inclusion. So we have a map actually. Yeah, we have a map. RQ modulo NQ to R modulo M power Q. It is an inclusion because this is precisely the kernel. NQ is precisely the kernel of this map. Therefore, it must be an inclusion. Conversely, RQ modulo NQ is a field. Therefore, any homomorphism must be an inclusion. So we have ultimately this. So hence R, remember what we started with? We started with MQ mod MQ square. And by a series of isomorphisms, we have arrived at this setting where NQ mod NQ square is a free RQ or NQ module, which if you tensor with another ring, which is an extension of this ring, we have just shown that RQ, this inclusion holds. So if put very simply, if Rn is a free module, you tensor it with S over R is a free S module. So this particular thing is a free R modulo M power Q module. But what is it isomorphic to? It is isomorphic to MQ mod MQ square. So the conclusion is that MQ mod MQ square is a free R mod MQ module. And observation, this is a very easy observation, it's that a set x1 through xn of elements in R is like independent if and only if, so if and only if the ideal I x1 through xn is such that I mod I square is a free R mod I module. So this is actually very easy to check because when do you say that I mod I square is a free R mod I module? When there is no linear relation in that particular ring over or within that. So yeah, you can easily check it yourself. It's not, while it may be very. I may confuse you if I start talking about it now, but um, yeah, it's easy to check. Just look at what the property of like independence means, and then yeah, you can work out the corresponding. Basically, you have a1 x1 plus an xn. 0 implies ai belongs to this x1 through xn. And that in R mod I is precisely that ai themselves must be 0. So there is no linear relation. And these are all R mod I linearly independent elements of I mod I square, and they also generate I mod I square, therefore they are basis. Conversely, if I mod I square is a free R mod I module, then those set of generators must generate the ideal I, and this they must be like independent by the linear independence. So it just follows directly from the definition. That was our motivation. Okay, so we wanted to show that this is a free R mod MQ module, MQ mod MQ square, and so a set of generators, minimal set of generators for MQ must be like independent. Okay. Um, okay, maybe I should just qualify this. I will have to. If and only if uh, the ideal here I is minimally generated by x1 to xn. So that is the observation. And this is so, yeah, our proof is almost done. So let x1 to xd be a set of minimal generators for m, then x1 power q to xd power q is a set of minimal generators for mq. And so uh, these sets x1q to xdq is like independent. And also length of r modulo mq r, what is this then? We have a formula for additive which gives us uh, a length of independent sequence. Here they are just powers of q. So by additive property, we can just say that it is q power d times length of r modulo x1 to xd. But what is x1 through xd? It's just a set of minimal generators. So this is q power d times length of k, which is just q power d. Okay, so we know what the length of r mod mqr is. And completion does not change the length. It does not affect the length, which is because there is a much more general property regarding length and faithfully flat extensions, which I'll just leave you to check in Matsumura. But all that we have to know now is that this is just, they are equal. Okay, so now, yeah, hence q power d is equal to this length. Okay, and this is true for all q equal to p power e, because e is any integer larger than at least one. Okay, so we want to know that r hat is regular, because showing that r hat is regular will imply that r is regular. And to show that r hat is regular, we again will have to go to completion, and then we have to use cone structure theorem to say that even in this case, it's equi characteristic because our ring is of characteristic P. So rings of characteristic P are always equi characteristic. So by cone structure theorem, this is like this for some, this is a quotient of some power series ring over field. Uh, yeah. Okay. Wait. Let me just change the symbol. Yeah, y1 to y3 because we're using x1 to x3 for the generators of maximum. And let capital M be the ideal y1 to yd. And by Krull's intersection theorem, we know that the intersection of q equal to p power e greater than equal to 0 is a 0. It means that if you take the intersection of all powers of m large enough, then they must intersect at 0. Like, yeah. So if I is non-zero, then there exists a q such that I is not contained m power q, which is just y1 power q to y d power q. Also, uh, note that m power q uh, r hat is our m power q r hat, because yeah. So the maximal ideal of the power series ring in R hat is precisely its maximal ideal, and therefore this equality holds. And this line is because we just saw that the intersection must be zero, therefore if I is non-zero, then there is some large q. Uh, so there is some q large enough such that it's not contained. We have then um, okay, one final nice thing that I have to uh, note, that D here is what we call the embedding dimension of R hat, which is mu of m being the maximal idea. So this D is the same as this D here. Uh, this D, it's a y1 through yd. That is precisely the same D which appears here. That is because the completion, the core structure theorem works something like, we will look at the set of generators and then we will map the elements, generators of regular local ring to those generators of maximal ideal. So the D's in both cases are the same. So then we need to use the formula for length and somehow show that there is a contradiction. So that's what we're going to use. This length of R hat of R hat modulo x1 q to x dq r hat, which is length of this k x1, so not x1, y1 to yd modulo I comma y1 power q to yd power q, which is strictly less than length of k y1 to yd modulo y1 power q to yd power q, which is actually equal to q power t. And this is a contradiction. So this strictly less than comes because I is not contained in y1 power q to yd power q. So that is the reason why there's a strict inequality symbol, but we can't have that. Both sides are q power t. Hence, I is 0, hence r hat is regular, and so r is regular. And that is the proof of Kunz theorem. Okay. So, right, I wanted to talk about a result on Hochster-Huneke. It might take some 5 to 10 minutes. Is that fine? Or do you want to end the meeting now?
You can continue.
Okay. Yeah. So this is a sort of corollary, which is very interesting. So let me just give uh, some basic results which we need. So the following proposition is from theorem 7.4, 7.5 of Matsumoto. It's a result on flat extensions and its properties. So let f from R to S be a flat map, and I comma J be ideals of R, X in R be an element. We have some equalities when it comes to flat maps. Okay, so I colon X, f of this times S is precisely f of I colon f of X in S. F of I, yes. This is the first equality. Generally, this equality is just a containment, it's not an equality. But because this is a flat extension, we can say much more about this. If I colon j dot s is f of I s intersect with f of j s. And the third is if f is faithfully flat, then f of I s intersect with r is just like, okay. So typically these results are just containments, but in the case of flat maps, they are equality. And this is a fact that we need now. So as a corollary to Kunz theorem, let R be a regular ring. Then for I comma j ideals of R, X in R, we have I colon X, the qth Frobenius is IQ colon XQ. This is the first result. And the second is I intersection J power with the qth Frobenius is precisely IQ intersect with JQ. So this is only true for regular rings. So now we will look at the theorem of Hochster and Huneke, which is the following. Let R be a regular ring. We are not assuming it to be local, it's a regular ring. Then every ideal of R is tightly closed. Tightly closed means that I is equal to I star, where I star is the tight closure of that ideal. Okay, so we will see why that is the case. Let I inside R be an ideal. Let X be an element in I star. So by the property, there exists some C in R naught such that C in R naught and some E naught greater than or equal to 1 such that C x power q belongs to IQ for all, let me just write it as P power C x P power E belongs to I power P power E for all E greater than or equal to E naught. And by corollary, therefore C belongs to, maybe I'll just write it on the page. So by corollary above, the C belongs to I P power E colon x power P power E for all E greater than or equal to E naught. Right? Therefore, C belongs to the intersection over all E greater than or equal to E naught of this particular colon ideal, x power p power E. Okay, so okay, maybe instead of the Frobenius power, maybe yeah, it's so this is which is contained in uh, I colon x power p power E. This is due to the corollary, and yeah, this is where the corollary is used, and this is contained in I colon x, the ordinary power for all E greater than or equal to E naught. Therefore, C belongs to the intersection E greater than or equal to E naught of I colon x power p power P. Okay, this is going to be important. Now, suppose we want to show that x belongs to I. So we assume that x is not in I by way of contradiction. Uh, just wait a bit. Let's say by way of contradiction. Then I colon x is a proper ideal because one is not contained there. Hence, it is contained in some maximal ideal m of R. Hence, the I colon x power p power E is contained in m power p power E for all E. Therefore, C belongs to m power p power E, where E is greater than or equal to E naught. If we look at the local ring Rm uh, by Krull's intersection theorem again, by Krull's intersection uh, theorem, power p power E where E greater than or equal to E naught Rm is 0 dot Rm. Precisely what it says is that powers of maximal ideal, if you take the intersection for all larger than some finite, all but finitely many intersection of maximal powers of maximal ideal, that must be 0. So therefore, C is 0 in Rm, and this is going to be important. Hence, there exists some T in R minus M such that T, yeah, T, such that T times C is 0 in R. That is, C belongs to associated the union. So C is a 0 divisor in R. Hence, C belongs to the union of all primes, so P belongs to associated prime of R. But remember how I told you that the R is regular rings are reduced, therefore associated primes are all minimal. And this is a contradiction because C belongs to R naught, which is precisely R minus the union of all primes, P being to P. Okay, so yes, hence our assumption is wrong, and the element x belongs to I, and therefore I is equal to I star. and that is the result of Hochster-Huneke. So this is actually a very fascinating property of regular rings, which I'll just define. So ring R is weakly F regular if every ideal I of R is tightly closed. That is I equal to I star. And uh, it it is still an open question whether this weakly F regular property localizes. So until then, we will have two distinct notions called weakly F regular rings and F regular rings. So R is F regular if for every multiplicative multiplicatively closed set W in RW is weakly F regular. So it is still open whether F regular and weakly F regular rings are the same. That is, F regularity, the weakly F regularity is a local property. So until then, we will have these two distinct uh, definitions. And the corollary is regular rings are F regular. Why? Because regularity is a local property. So if R is regular, then for every multiplicative closed set, R localized W is also regular. And we apply that the Hochster-Huneke result here. We apply Hochster-Huneke's result to RW and see that, of course, in RW, every ideal is tightly closed. Therefore, RW is weakly F regular. And so by definition, R is F regular. Okay, so let me just stop here. And that is my that's what I wanted to talk uh, in these four sessions. And from next week, Aditya will talk about this weekly F regular and F regular mix. Any questions or doubts? So if you have any doubts in the exercise tutorial sheet, you can also ask me here now.
Uh, is the talks
Yeah,
are going to be at the same time or we are going to different time
I
from
think
next?
you have to ask Aditya
Okay.
because I wanted to have it at this time because it's convenient for most people. But uh, yeah, Aditya will post it in the group and yeah, whatever time is convenient for you, you can
Okay.
message them directly if that is also convenient.
Okay.
Okay.
In the last
Yeah.
theorem, I have one question. In the last
Yeah.
theorem, uh,
Hope you okay.
yeah, this theorem, the
Yeah.
curves into intersection theorem you used there.
Yeah.
How did that
Oh,
follow?
what is your question again?
Krell's intersection theorem you used
Yes.
somewhere in last theorem.
Yes. Yeah.
So,
Ah.
but
Oh, you were
intersection
asking
should run over all E or
greater than
after
or equal to E naught.
sufficiently large.
Yeah.
But Krell's
So
intersection theorem, intersection
it
of all
is
powers of maximal ideal, right?
all powers, yes, all say so just substitute. So intersection of m power n greater than or equal to 0. Of course, this is 0. That is Krull's intersection theorem. But
Yes.
this uh so note that m contains m square contains m power some e naught. Therefore, intersection of m where m power I from 1 to E naught is just m power E naught. Is that fine?
Mm, yeah. Yes. Yes.
Which
Okay.
which means that intersection I from 1 to infinity m power I is precisely you can take it from I to I naught itself. Yeah, and both these
Okay.
intersects are same. Yeah.
Yeah.
Okay. So yes.
And I have one more question. It is not clear to
Yeah.
me. Like
Yeah.
whenever you are taking that Frobenius map is flat,
Yes.
so we are seeing it through the Frobenius map as a R module. So we want to see whether
Hmm.
this map is flat or not. But if you take
Yes.
the image of the Frobenius map, that is R to the
Yes.
power q, so it is
Yes.
inside R also. So
Yes.
so as a subring, R to the
Yeah.
power q is subring of R. So we have a
Yes.
action of R to the power q over
Ah.
R. So
Yes.
as a that module, it is flat. Is same as saying that if the Frobenius map is flat.
Uh, that was precisely the point I wanted to say. Like, I mentioned this last time that there are examples when the image, the inclusion is flat. So I'll be more precise here. So let F be not F. Let R be the ring. Some FP x modulo x square. Okay. Now, if we look at the Frobenius map, R to R, then this takes x to x power p. The image R power p, if you look at it, it's precisely fp. Why? Because x square is taken to x power 2p, but x power 2p is what? X power 2p is just 0 because anything x power p. X is taken to x power p, but this is 0.
Okay.
And so R power P is Fp, and R
No.
power P inside R is a, flat extension. In fact, free because R power P is Fp. So you're just looking at R as a module over a field, and it is going to be free anyway. But
Okay.
but the Frobenius map is not flat because if it is, then F is faithfully flat. Why? Because this is a local ring. R is a local ring. Therefore, flat implies faithfully flat. Hence, F must be injective. Faithfully flat ring maps are injective. But
Okay.
uh, hence, R must be reduced. The Frobenius is injective if and only if the ring is reduced. But this is not the case
Okay. So
because
whenever
since
we are in the reduced case, we can say this, right?
since x square is 0. In the reduced case, the Frobenius is injective.
So
And
then we
so
can say that, right?
And yeah, so whenever you have an injective map, you can identify the source ring with its image by an isomorphism. So if P from R to S is a ring map, is an injective ring map, then R is isomorphic to phi of R inside S. Hence, R to S is flat if and only if P of R to S is flat. Okay.
Okay.
And that is the whole point of this. That is the whole reason why we can assume that we this particular extension is flat or not. We can just prove that and be done with it. Because in our situation, when R is regular, R is reduced, therefore the Frobenius is injective. Conversely, if the ring map is flat, then it is also faithfully flat, hence the Frobenius is injective. In both cases, Frobenius is injective, and therefore we can work with the subrings and all that instead of looking at the map directly.
Okay.
Okay.
And while proving the Kunz theorem, the if part, so you are
Yeah.
reducing it to the local case.
Yes.
So the Frobenius map localizes like if because if
Yes.
you
Yeah.
take
Yeah. Yeah.
r by t, then it goes to
Huh.
f of r by t. F of r is r to the power p by t.
Yeah.
So
Yeah.
it's is it same as r by t to the power p?
No, that is not what we are saying, right? So uh, the if the Frobenius map, if
Yes.
you have a map from R to R, right? So where
Okay.
R is taken to R power P in uh, RW to RW, where you have an element RW, it is sent to R power P more by W power P. Why would
Yes.
it go to R power P by W?
No, no. So
Oh,
so you what when you localize the map, so what is the localization map? S-
you are
So
not you are not localizing. So how do you first localize any ring map? You just you take this to suppose you have a map from R to S, and then you want to localize, say, P to P intersection R. What you do is you take, how do you get this equality? You take R to S localized at P, and then observe that any element in P intersection R is a kernel, is a unit in SP. Therefore, you have an induced map by R localized at P intersection R to S power SP. This is the whole way, the basic way how you get localized maps. And we apply the same thing to the Frobenius. So the Frobenius from R to R, you then send it to R localized at W. And if you look at the pre-image, uh, if you look at elements of W, they go to units in
mm,
RW. Therefore,
okay.
by induced map, you get RW to RW, where
Mm,
by the default property W is taken to W power P anyway. That is the whole point of this map here.
okay. So in
And
this
so,
way, it is Frobenius map. But
yes,
usually, whenever we say that Frobenius, we check flatness properties. So if you have
yeah,
a map from R to R, so you define the
yeah,
map S inverse R to S inverse R.
yes.
Usually, what we define that S inverse F, the if the map, so the new map is it is sending R by T to F of R by T. That's what I was asking.
No, no, F applies to both numerator and denominator.
It applies to both numerator and denominator. That's the point I'm making. Not just the
Okay.
numerator, it applies to both numerator and denominator. And I
Okay.
think this was also mentioned in one of the, I think I left it as exercise in the first session, I think.
Okay, okay.
Uh,
Sorry, I was confused a bit. Okay, it's fine.
I think, yeah. So this is the Frobenius push forward isomorphism where it is sent in this fashion. But yeah, that is the whole point. Like Frobenius is it whether you go via the induced way or you just take it the normal way, both of the give the same result.
Okay.
Yeah.
Viram?
Okay. Yeah.
So